Human imagination is fluid, messy, and infinitely complex, but a computer processor, it only understands the rigid, binary reality of electrical switches being turned on and off. In the 1940s, bridging that gap meant the human operator had to do all the heavy lifting. Early computers didn't have keyboards or screens. To tell a machine what to do, you had to physically conform to its architecture. Look at the sheer scale of the ENIAC. Female mathematicians like Jean Jennings Bardick spent days manually routing thick cables and configuring plug boards by hand just to calculate a single artillery bullet trajectory. This process was painstakingly slow. It required an elite understanding of the specific hardware, making computing highly exclusive and impossible to scale for general use. If we had to keep programming in raw machine language, the digital revolution would have stalled in those massive rooms. We desperately needed a way to translate human intent into machine action at scale. By the 1950s, we built the first automated bridge, the compiler. Instead of plugging in cables, a programmer could type English-like text, feed it into the compiler, and let the software filter it down into the ones and zeros the processor actually understands. Pioneers like Grace Hopper led this charge. She developed COBOL, a language that allowed operators to issue commands using familiar words and math symbols rather than obscure machine code. Over the decades, this text abstraction evolved rapidly. The syntax became cleaner and more readable, eventually giving us modern scripting languages like Python and JavaScript that look almost like plain English. These high-level languages successfully opened up programming to millions of developers, but typing rigid lines of code still alienated the general public. People don't naturally think in command-line syntax. We operate spatially. To solve the spatial problem, Douglas Engelbart invented the computer mouse in 1963. For the first time, a user could physically point at something on a screen to communicate with the machine. A decade later, the 1973 Xerox Alto combined that mouse with the first graphical user interface. It took raw, hidden code and turned it into interactive visual metaphors, like documents and folders, that anyone could recognize. Apple's 1984 Macintosh polished this concept for the consumer market. It completely replaced the need to memorize and type commands with the intuitive, universal action of pointing and clicking. By translating complex mathematical operations into simple human actions, the graphical interface successfully brought computing power to the masses. Today, we have vibrant touchscreens and highly readable programming languages. Yet, as we push into the era of artificial intelligence, we have hit a massive new translation wall. We call it the two-language tax. AI researchers build their prototypes in Python because it's incredibly easy for humans to read and write. But Python is too slow for production, so the code must be completely rewritten in low-level languages like C++ or CUDA to actually run fast on machine hardware. This disconnect carries a severe real-world cost. It splits engineering teams in half and drastically bottlenecks AI development, simply because the language the researchers use cannot efficiently talk directly to the GPUs processing the data. To fix this broken bridge, developers built a unified programming language called Mojo. Mojo is designed to offer the exact same clean, readable syntax of Python, but under the hood, it natively translates those instructions down to the bare metal, high-performance speeds you would expect from C++ or Rust, across both CPUs and GPUs. By eliminating this two-language tax, we remove the modern friction of translation. Human creativity can finally execute at maximum machine speed, without compromise, and without having to rewrite a single line of code. When we step back and look at this historical trajectory, the pattern is clear. We started with the most friction-heavy forms of data entry imaginable, punching physical holes into paper carts. Then, industrial designers like Henry Dreyfuss argued that we must fit the machine to the man, rather than forcing the man to fit the machine. Computer science operates on a trajectory toward the invisible. Every major breakthrough seeks to hide the mechanics of the machine from the person who operates it. We are now entering the era of zero UI. With the rise of AI generation and advanced natural language processing, we are bypassing traditional tools, drop-down menus, and syntax entirely. We just speak, and the machine responds. This rapidly approaching reality mirrors a vision first outlined in 1945 by Vannevar Bush. He imagined a device called the Memex, which he described as an enlarged, intimate supplement to human memory. As translators become nearly flawless, the computer ceases to be a cumbersome tool we consciously operate. The barrier between intent and execution dissolves. Erasing this final layer of translation allows the distinction between machine and mind to evaporate. The computer settles into its final form as a seamless, immediate extension of human thought.